Hi, in this tutorial we will study some notes that summarize how is that we find candidate keys from functional dependencies, what is a relation decomposition, and when a decomposition is lossless. You check the PowerPoints provided for this lecture, you will see that there are two methods that they are discussed to find candidate keys. What we need is a set F that contains functional dependencies. Those functional dependencies are are valid in a given table. So what we need as an input is a table or a relation, which is in this case R with attributes A1, A2 up to AN, which is the same as table R with columns A1, A2, and so on. And then the ZF contains the functional dependencies. In method 1, what the PowerPoint discusses is that we can find the closure of all possible combinations of those attributes. Like for example, all single attributes, like for example, is A1 candidate key. If it is, then I mean, if we compute, I'm sorry, A plus, and if A plus derives all attributes of R, then it's a candidate key. And now then we combine A1 with A2 and A1 with A3 and so on, and see if we find the candidate key. In the worst case, all attributes can be the candidate key. On method 2, that discuss the dependency graph. So I will show you some examples to illustrate those methods. So what I think is the best is to combine some from one method and from the other. But let's see the following example. In this example, this is the table that we have. We have table R or relation R that has the attributes A, B, C, G, H, I, and this is my set F that contains 1, 2, 3 functional dependencies. The question is, using that information, find all possible candidate keys. Now here I will illustrate the main concepts of these methods. In one of the methods, they ask us to define what is a dependency graph. The dependency graph is constructed with the functional dependencies that are here. For example, here we got A implies B and C, and this is what we have in the chart. You see the first functional dependency A, and then those two arrows that go into B and C, and then we got the C and G together derive H and I. So this is how in my chart I have the C and the G together get the H, and then in the other side gets the I. Then the other one I got the B derives H, which is what I have here in the graph. So this graph, what we see, which is my dependency graph, captures the information about the given by the set of functional dependencies. Now, one way of inspecting is if there is an attribute, a combination of attributes that we can, that from that point we can traverse the whole graph and find all attributes. Now, something else that was discussed in the PowerPoint that says, okay, find from this chart, from this graph, the nodes that has no incoming, and this is the one that we have here. The B that says no incoming is G, is A, I'm sorry. Why? Because A doesn't have any incoming edges, and G is the other one that doesn't have any incoming edges. Now, the ones that are only incoming is H and I. You see, there is no outgoing from there, and then it's nothing from I. And then in the PowerPoint also says that A and G is very important because there is no incoming, so they need to be part of a candidate key because there is no other way of deriving them. If they two together, I mean, if one by itself is not a candidate key and the other by itself is not a candidate key, but they together is the candidate key, they should be then the only candidate key. Now, H and I, since are only get incoming, they should not be part of any candidate key. These are attributes that can derive from someplace else. So now let's look at A. If we do the A plus, or we go and look at the graph A, from A I can get B and I can get C, and from B I can get H, but then I cannot move any further from that side because to go to G I need I don't have any way of going to G. You see I get stuck, and then I'm not able to get I because to derive I need to have the G and I don't have the G. Then A is not candidate. The same with G. You see if I'm in G, it's even worse than A because from G I cannot derive anything because I need C to move. However, if we got the A and the G together, we can derive the other attributes. Look here at the graph. Or the other exercise that we can do is compute the AG plus, and we will see that AG combines all the attributes. So AG is the only candidate key. Why? Because all the attributes from this set, the BIN, together become the candidate key. I mean, A by itself cannot be candidate, G by itself is not candidate. Then they together are candidate, then it's the only candidate key. All that information is described in the PowerPoint. Let's look at the second example. In this second example, I have this table R with A, B, C, D, E, H, and then 1, 2, 3, 4 functional, 5 functional dependencies in my set F. What I will do is, again, we get the dependency graph. So again, A derives B is indicated there. Then A and B together get the E. That's what I have here. B and H gets C, and C by itself is D, and D gets A. Now identify the ones, the set V and I, which is no incoming. The only one that doesn't have any incoming is H, which means H has to be part of every candidate key. Now, if H by itself is candidate key, then H is the only candidate key. If we look at the graph from H, I cannot move and derive anything because I need the B. Then H is not candidate. That means there are other candidate keys. There will be more than one candidate key in this case, probably. So E is the one that has only incoming, so E cannot be part of the candidate key. So now let's see, B and H together get C, and then from C I can get D, and from D I can get A, and then from A, since I have already B, I can get E, so I can get everything. So the combination of B and H is candidate. How can I be sure again that there is nothing else? Well, we already know that H by itself is not candidate. B by itself is not candidate either because you cannot move from B. So HB is one of the candidates. Now, if we expect, for example, A gets A, B, but it doesn't move from there, and if I get the H, then I can get all the other attributes like I said before. So the other candidate keys by inspecting this graph is HB, HR, A, HD, and HC. And you see all candidate keys contain H, which is the elements of the set B and I. So what was the difference with the previous one? That A and G together was the candidate key. So that's the only one. So again, if H were candidate, then H will be the only candidate key, but H wasn't candidate. Now, the other concept that we have to review is a relation decomposition. Remember that the main topic for this chapter is normalization. So for normalization, we will decompose tables that we consider that are not good tables. So we obtain what a possible normal form that we're going to call BCNF or 3NF. So first we need to review the concept of decomposition. Decomposition is the following. So for example, here we had the table product manufacturer, and then product number, product name, price, product manufacturer ID, manufacturer name, and address. And then I'm just illustrating this because sometimes we get confused that we use R, A, B, C, D. This is just for simplicity. So what we're talking is, and then we have here a functional set of functional dependencies that says product number determines these other attributes, and then the other functional dependency manufacturer ID determines those two attributes. When this is okay, but we prefer to use letters to make things easier. So for example, R is A, B, C, D, E, F, and then I know A means product number, B means product name, and so on. So F, if I do that conversion, then this is the same as having this R, A, B, C, D, F, and so on. So I have these two functional dependencies. Now, the concept that says that the composition is that we have then two possible tables, right? And then here they're presenting a decomposition that we're calling the set M, which is my table R1 and my table R2. Now, the other concept is when we have a decomposition, we ask for the question if this decomposition lossless. Lossless means that we will not have any attributes that were not there before, because this is the original table. And then If we do the, and we're dividing table R into table R1 and R2, and then if we want the original table, the information that we got before, then we should do the join between R1 and R2, and then we should get R, but nothing extra. When we get something extra, then we say that the table is lossy. Let me, well, I will show you the power. Well, you can check that in the PowerPoint. In the PowerPoint, there is an example of a table that once you do the join, you got additional rows there that were not there before. Okay, so the question for this exercise is M, the set lossless join decomposition. So I'm rewriting M in the following way. So M is this set, R1 and R2. Again, this is the composition of the table R, which is this. So that means if we do the join with R1 and R2, we're getting back R. When we decompose, remember the information that is in the table is okay, but we're decomposing, and then if I need that information back, we do the join. So the way that we check, there is a procedure there that says look for the intersection of the attributes in R1 and R2, so it's D, and then see if that attribute can derive the other from the other tables. In this case, that's what we call R1 minus R2 or R2 minus R1. So if D can derive A, B, C, or D can derive E, F, then the decomposition is lossless. So D will be like kind of like the foreign key. So why is that we're doing this? Because then D will act in that table like the primary key. So for example, if D will be the act like the primary key in R2, then D should derive E and F. That's what it means. Or here, if D will be like the primary key here, then D should derive A, B, or C. If we have that, if we decompose on an element that can be the we do the join with an element that can act like foreign key, means that it's the primary key in the other table, then the decomposition is lossless. So in this case, we check, is D deriving A, B, C? So we check like we already did with the previous examples. We can do the D plus, or from here, for example, there's a D derives D, E, F, and then nothing else. It doesn't derive anything with A, B, or C. So that's wrong. Now, can D derive E and F? We check on here, and it's actually one of the functional dependencies. You see the second functional dependency is D derive EF, and we got a yes. Therefore, the decomposition M is lossless join, and that's what we want for this. That's the concept that we wanted to review here. Thank you.